Hi everyone, in this video we're going to go through the strategies needed to solve inclined plane problems. Alright, so the first thing is that we want to tilt the axis so that the acceleration is only in the x direction. Alright, so what that's going to look like is we know that the block is going to accelerate down the ramp in that direction. And then we're going to make that the x direction. Okay, positive x is going down the ramp, which means our y will have to be tilted as well so that it's perpendicular to the surface. Right? And once we do that, we can label our forces. Okay? So in this situation, we're just going to have the block on a frictionless plane. Here we have gravity acting from the center, and that still acts straight down. G. Then we have the normal force from the surface. All right, and those are the only two forces that are acting on this block. So why does it go down the ramp? Well, if we look at it from this perspective, it is the x component of gravity. That should be mg, by the way. So it's just the x component of the gravity that is directed down the length of the ramp. The next thing that we have to take into consideration is that angle. All right, that angle theta is going to be the same angle that goes here between the weight and the y-axis. All right, there's geometry that can go ahead and prove that. If you are curious, you can ask me how that works out or figure it out for yourself. But the angle of the ramp is going to be the angle in between the y-axis and gravity. So that would be theta right there. And if we do those two things, the rest of this is cake. All right? So we have to go through the rest of our problem-solving process. So we look in the x direction, and we sum up all the forces in the x, and we decide, is it accelerating? Yes, it's going to accelerate down the ramp. So we're going to have an acceleration only in the x direction. And that's really why we tilt this acceleration, or tilt the axis, so that we only have an acceleration in one direction. How many forces do we have going left and right? Well, again, we have to think about the tilted axis, and the only force we have going left to right is that component of the weight. Right, the two components that we have the downward y right here, and then we have the horizontal component there. So this is the one that is going to accelerate the block down the ramp. Now, how do we find that? Notice that this is our angle right here. Now, this side, which is the x component, is now opposite the angle given. So if we have the hypotenuse and we need the opposite of the angle, that's going to be the sine function. So really, that's the third thing that we have to consider when doing inclined plane problems. All right, so now, because our angle is with respect to a y-axis instead of an x-axis, what's going to happen is we use the sine for the x components and the cosine for the y, so it flips. Okay, so the x component of mg is going to be the hypotenuse times the sine of that angle theta. And that is the only force that's going to cause that mass to accelerate. We can now look at the, oh, I messed that up, the y direction here. I can't move my words. All right, let's throw those off to the side here. Let's see what happens with that. Okay. So now let's add up all the forces in the y direction. So if we sum of all forces in the y, is it accelerating up and down off of the ramp? Is it going up and down off the ramp? No. It's staying on that y-axis location, so that the sum of all our forces in the y is going to equal 0. How many forces do we have acting in our y direction? 2. We have the normal force going up, and then we have the y component of gravity going down. And that is going to be mg cosine of theta equals 0. And then if you look at that, you only have 2 forces going in the y direction. So the up force has to equal the down force. All right? So our normal force is going to be less than the mg, the normal weight of our object, because you're multiplying by the cosine of an angle, which is always a fraction. So the normal force is only going to be a fraction of the weight. The more you tilt this ramp, okay, it's going from what a 0 angle, which is level. Here, maybe I can draw that out. All right. So if we had a level surface, right, we have the normal force equals mg. But as we increase the angle, the normal force becomes only a fraction of the gravity. Increase it some more, all right, that y component of gravity decreases until it's vertical, and then the block will just fall straight down, and there will be no normal force. All right, so it goes from its max of gravity at rest. As the angle increases, it'll decrease to a value of 0, right? So that if the angle in between the normal force and gravity is 90, cosine of 90 is 0. All right, so that's a generic setup of a problem. I don't actually give you numbers or anything like that right now, so there's nothing to solve for. It's more about setting up the problem. All right, so let's make a problem with numbers and values and try to solve for something. Okay, here's a problem. So now, put some numbers here. We have a 2 kilogram block. The angle of the incline is 30 degrees from a horizontal line. So whenever it says from a horizontal, if we draw a horizontal line here, this will be 30 degrees. If we draw a horizontal line here, that'll be 30 degrees. So it's just with respect to any horizontal line. Okay. We want to figure out the normal force on the block and the rate of acceleration of the block. What's different from on this one than from my example is that there is friction. All right, so we're going to add a force to this block. All right. First thing I'm going to do is draw out my free body diagram. I'm going to draw it off of the picture there. So there's my block. I'm going to tilt my axis. I'm going to draw my tilted axis there. So this is my x and this is my y. All right, I have gravity going straight down. I have the normal force acting perpendicular to the surface along the y direction. And then I'm going to have a frictional force up the ramp. Okay, and the angle is going to go between the y-axis and gravity. So that's the first thing. Always draw the diagram. Second thing is identify your law. So I'm going to solve for the normal force. The normal force is only in the y, so I'm only going to worry about the y for right now. The block is not going to be accelerating up and down off of the ramp, so that means that the sum of all the forces up and down are going to be 0. Now I only have 2 forces. I have the normal force up, and I have the y component of gravity going down. All right, so I have the normal force up minus the y component of gravity down. Now, again, that's the adjacent side to that triangle. The triangle has to match up with the dimensions of the axes. So we have a y component along the y-axis, and we're going to have an x component along the x-axis. Right there. And it makes a right triangle where those components intersect there. All right, so it has to be this x-axis, that has to be parallel to it, and then that has to be parallel to the y. Because it's the adjacent side, it's going to be the cosine function that's going to give us the correct value, and that has to be 0. So the normal force is going to be equal to the weight times the cosine of the angle. All right, now that we have some numbers, we have 2 kilograms times 9.8 meters per second squared times the cosine of 30. Right. So again, the weight itself is going to be 2 times 9.8, and that's going to be 19.6, right? So we're going to have 19.6 times another fraction, and that'll give us like 16.97, so I'm just going to round it up to 17 newtons for the normal force. All right, so it is less than the 19.6, which is mg. Okay, the next part is to solve for the acceleration. So I'm going to get this stuff out of here. Probably going to mess up my diagram. Nope. All right. So now let's sum up the forces in the x, and we know it is going to accelerate down the ramp. All right, we have 2 forces left and right. All right, we have the x component of gravity, it's still there. And since that is in the direction of the acceleration, down the even though it's down the ramp, it's still to the right. We're going to make that the positive because we want the object to accelerate in the positive. All right, and because it's the x and our theta is going there, it's the opposite side, so we're going to use the sine function. And then we also have the frictional force going backwards, and that equals ma. All right, so we're looking for a. We just have to divide both sides by the mass, and then plug in our values, right? So we already did the calculation for mg, and that's 19.6, and then it's the sine of 30 minus 2 newtons all over the mass of 2 kilograms to give us our acceleration. And if I did that right, I get 3.9 meters per second squared. All right. If we look at if there was no friction, the acceleration rate should be higher. So if you're able to just calculate that value, which is actually 9.8 divided by 2, I think you get 4.9. Yeah. All right, so we definitely have a slower acceleration than if there was no friction. I'm pretty sure we did that one right. Okay. We will add more to the friction part of this using our fun equation with our coefficient, and I'll do that in the next video.